Hi everybody and welcome to a new exciting video in the PyTorch for audio and music processing series. This time we'll get our hands dirty with PyTorch for the first time. In other words, we'll be creating a neural network from scratch and then we'll train it and then we'll save it. This will allow us to get an overview of the different parts of PyTorch. We won't be focusing on audio specifically, but rather on a toy dataset, the usual one that you always get when you are dealing with deep learning models for the first time, and that's the MNIST dataset. In other words, we'll be training an image classifier that will allow us to recognize different digits from the MNIST dataset. Okay. So before we get started, we need to install PyTorch. And if you haven't done so, you can launch your console and then install it via pip, doing a pip install. Then we'll install Torch, which is PyTorch, and then we'll install Torch Audio and Torch Vision, which has a lot of interesting packages and modules that we'll be using throughout the series. Okay, so you just run this. In my case, it's not installing because I already installed it, but you get the idea. The different steps that we'll be focusing on are this 5 over here that I'll just transfer. Okay. So first of all, we'll be downloading the dataset, and that's because the MNIST dataset comes directly with PyTorch. So PyTorch has an array of different datasets that you can use right off the bat, and we'll be using one of this, and then which is the MNIST dataset. Then we'll be creating a data loader, and you'll know more about what a data loader is throughout this video. And then you will build a model, and in our case it's going to be a very simple feed-forward neural network. We'll create code to train the model and finally to save the trained model. If you're wondering about inference and loading the model, well, that's going to be part of next video. Let's get started with downloading the dataset. Okay, so I'll create a function called download MNIST datasets, and I'm using the plural here because we'll be downloading 2 parts of the dataset. So one which is the train set and the other one which is the validation or test set. So here we'll have train data, and then for the train data what we want to do is get this datasets which I've imported from Torch Vision. So we'll do a datasets dot MNIST, and we need to pass a few arguments here. So first of all, we'll pass the root, and we'll put this one equal to data. So what is this? Well, basically we are telling PyTorch where to store the dataset that we are downloading, and in this case the dataset will be stored under a new folder called data, which will be created in the working directory. Okay, so now we have the root. Next we have download, and we'll set this equal to true, which basically means if the dataset has not been downloaded yet, please do download it. Then we'll have train, and we'll also set this equal to true. So here we are just saying to PyTorch that we are interested in the train set part of this dataset. And finally we have transform, and here we'll put transform equal to the toTensor object. So now transform is a very interesting argument because it allows us to apply some sort of transformation directly to our dataset. And in this case, we chose this toTensor, which I imported up here from torchvision.transforms. Now, what toTensor does, it takes this image in and it reshapes a new tensor where each value is normalized between 0 and 1. Now, you may be wondering, but what is this MNIST class all in all? Well, this MNIST class is a concrete implementation of a dataset class that comes with PyTorch. Now, a dataset class is really cool because it allows us to store in a very orderly manner all the labels, annotations, as well as the different sample data, and then use them for our training. So in other words, in this case, we have a concrete dataset class, which is MNIST, and which has already been implemented and is stored with PyTorch. Moving on with the series, we'll be implementing our own custom datasets, and there it's going to be nice and more advanced topic for sure. Okay, so this is about the trained data. What about the validation data, or the validation set? So yeah, we'll just copy paste the code that we use for trained data, and then we'll just call validation data, this one here. And the only change that we need to apply here is to train, and rather than saying train equals true, we'll say train equals false, which means, hey, give me the non-trained part of the dataset. In other words, the validation data. And here we'll return both the trained data as well as the validation data. Okay, now just a disclaimer, I will not be using the validation data. So we won't be using a validation set for our training, just to keep things extra simple. But here I just wanted to show you how to download both the train and test or validation part of a dataset from PyTorch. Okay, so now let's see if this works. So we'll create a script real quick. So if name is equal to main, then we'll download MNIST dataset. Okay, so let's go with train data, and here we'll just put an underscore because, as I said, I'm not really interested in validation data. And here we'll call the download MNIST datasets, and here we'll just finally put a print saying MNIST dataset downloaded. Okay, so now let me just run this in debug mode and see and show you here. Okay, so as you can see, the trained data is an MNIST object, and it has 60,000 samples. And then we have the validation part of it, which in our case is just the underscore, which again is an MNIST object, but it only has 10,000 samples. In my case, training the datasets was super fast, and that's because I already downloaded them before. And as you can see, when I run these download MNIST datasets function for the first time, I got this data folder created here in the working directory, and here you have like the MNIST dataset. Next, we want to create a data loader. You may be wondering, but what's a data loader? Well, it's a class that we can use to wrap a dataset. In our case, it's going to be the trained data, and it will allow us to fetch data, to load data in batches. And that's because a data loader is an iterable object. And so when we iterate through it, we load data in batches. This is fantastic because it allows us to load datasets that are quite heavy on memory without having any issues, because we're just loading them in batches. Okay. So now let's create a data loader for the train set. Okay, so here we'll do a train data loader. Now, I'm not really creating a function here for creating a train data loader, or a data loader more in general, because this is, as you'll see, super simple. So here we just call the data loader class, and we have to instantiate this class. If you're wondering where this data loader class comes from, so you'll see it up here. It comes from torch utils data. Okay, so here we should pass a couple of things. First, and of course, the dataset that we want to wrap, and that's our train data, and then the batch size. So the batch size, and we'll define this as a constant, and we'll just define the constant up here, and I'll put it equal to, yeah, let's say 128. Good. Okay, now I created a trained data loader. If we were to use also the validation data, we would have needed to create also a validation data loader, but that doesn't apply in our case today. Okay, so now we're done with the data loader. What next? Well, we actually have to build a model. So this is the core of this video, really. So how do we build models in a PyTorch? Well, the basic idea is that the models that you create are in classes which inherit from the module class that comes directly from PyTorch. Okay, so now let's define our class or our model. So as I said, we'll be using a very simple feed-forward network. So we'll do class and we'll call it feed-forward net. And we said that this class inherits from module. So we have nn.module. Now, nn can be imported directly from here. So from torch, import nn. Perfect. So for defining a model in PyTorch, we need to define a couple of methods. First of all, the constructor, and then another method that's called forward. Let's start from the constructor. So first thing that we want to do is to invoke the constructor of the base class in this, or like the module class. And then what we want to do is basically to store all the different layers that we need in this model as attributes for this class. So in this case, what I want to build is a very simple a model where we'll have an initial layer that will flatten the data, the MNIST images. So, and it will convert them into a one-dimensional array, basically. Then we'll have a couple of dense layers. So one is going to be like a hidden layer, and the other one is going to be actually the output layer. And finally, we'll apply softmax. So let's see how we can do this. So let's create the first layer, and I'll call it flatten. And here, I'll just assign it the flatten object from PyTorch. So just remember, this flatten is an arbitrary name. It could be whatever. It could be John or Henry, if you will. Okay, so next we'll be dealing with the dense layers. So dense layers. And here I'll apply a trick, because rather than having as many attributes in this class as the number of layers, like in this dense layers, I'll just have like a this dense layers attribute, which will contain more than one layer. Okay, so let's take a look at this. So we'll be using for this trick a sequential. Okay, so now what's sequential? Well, sequential is a facility that of course comes with PyTorch, and it allows us to pack together multiple layers. And the kind of like the things that's particular about sequential is that the architecture, it's sequential. So the data will flow sequentially from one layer to the next. Okay, so here we're talking about dense layers. So the first dense layer that we'll have is this linear layer. Now, if you're familiar with TensorFlow and Keras, linear is the equivalent of a dense layer in Keras. It's just a simple dense layer. And it has two main arguments. So one is the input features, the number of input features, and the number of output features is the second one. Okay, so for the number of input features here, we'll have 28 by 28. And why 28 by 28? Well, because I know that the images in MNIST are 28 by 28 pixels. So I'll just like multiply those two because they have been flattened by the flatten layer. And then in the output, in this case, I'd say, yeah, let's use 256 neurons. Okay, so here we have our linear or dense layer. Next, we'll apply an activation function, which is, in our case, let's choose rectified linear unit, or ReLU. Here we go. We apply ReLU, and then we have another linear layer, which is going to be our output. So we'll do nn.linear, and here the number of inputs is going to be equal to 156, and the output is going to be equal to 10. Now, why 10? Well, because this is the number of classes that we have in the MNIST dataset. Remember, so with MNIST, we have all sorts of digits from 0 to 1, and in other words, we have 10 different classes. The final layer that we want to implement is the softmax layer. Okay, so here we'll apply softmax, and we'll say that the dimension is equal to 1. Now, if you're not familiar with softmax, well, what it does, it's basic transformation. So in this case, it would take all the values that we have predicted for the different 10 classes, and then it will transform them in such a way that when you add them up, the sum will be equal to 1. It's sort of normalization, if you will. Okay, now these are all the different layers that make up the graph of our network. Now, the next step is that of defining the forward method. And this is very important because it will allow us to tell PyTorch how to process this data. So here as an argument, we'll have input data. So in other words, what forward does, it explains or it indicates PyTorch how to manipulate the data in what sequence. And in our case, what we'll be doing is, first of all, we'll take x, which basically is going to be equal to the flattened data, and that comes out of self.flatten, and we'll pass in the input data. So in other words, we are passing input data to the flatten layer, and we'll get out this x. Well, yeah, let me just rename this because it could be clearer. So flattened data. Okay, yeah, I like this more. Then we'll pass the flattened data to the dense layers, and we'll get back logits or outputs. So here we'll do a self.dense layers, and we'll apply the dense layers to the flattened data. Good. And finally, we'll get our predictions by passing the logits to our softmax. So we'll do a self.softmax, and we'll pass the logits. Cool. And so now we are ready to return the predictions like that. Okay, so here we have our first ever neural network implemented in PyTorch. So just to have a quick summary, when you implement a model in PyTorch, what you want to do is to inherit for your class should inherit from module, and then you should have these two methods. So the constructor, where you define all the different layers, and then the forward method that specifies the data flow or the forward pass for your network. Okay, so now let's actually build the model here in our script. So we'll do a build model. Okay, so here we'll have a feed forward net. This is going to be equal to feed forward net. So we'll just instantiate feed forward net, our class, but then we have to do an extra thing, which is assigning our feed forward network or our model to a device. Now, what's a device? Well, in this case, we can have two devices. So one is CUDA, the other one is CPU. So if we are using GPU acceleration, then the device will be equal to a string called CUDA. Otherwise, we'll have a string called CPU. And that means that the model will be trained on CPU. Okay, but how do we determine which device to use? Well, we should check what type of acceleration. So we should check whether CUDA acceleration or GPU acceleration is available. So, and for that, we can use an interesting method that comes directly with PyTorch. So we'll do if torch.CUDA is available. So in other words, if GPU acceleration is available, then we'll assign to device CUDA. But if that's not the case, then the device is going to be equal to CPU. Okay, so now let me print. So with an F string, I'll say using device. Okay, so now I'd say let's run this and see which device we are using on my machine. Let's go. Okay, so and as you can see here, I have GPU acceleration, so I'm using the CUDA device. Good. Okay, so now we are done with the creation of the model. The next step is that of training the model. So for that, we'll be using two distinct functions. So the first one we'll call train one epoch. And for now, we'll just pass this. And then we'll have another function called train up here. Okay, so train is the kind of higher level function and which will use train one epoch. So in other words, in train, we'll go through all the epochs that we want to train the model for, and we'll be calling at each pass or each iteration train one epoch. Train one epoch, on the other hand, is actually training one epoch of our model. So let's implement this one, the bottom, the lower function first. And so here we have a bunch of arguments, quite a lot actually, that we should pass to train one epoch. First, of course, the model. Then we want the data loader. Then the loss function. Then the optimizer. And then the device. Okay, cool. So here, the basic idea is that we want to create a loop, and we'll loop through all the samples in the dataset, and at each iteration, we'll get a new batch of samples. And this is where the data loader comes in very handy, because it's an iterable which will return us both the inputs and the targets, or in other words, the x's and y's for one batch at each iteration. Okay, so here we'll do for inputs, targets in data loader, and here inputs and targets are not really ready yet to be used. So what we should do is something that's quite annoying. I find it quite annoying in PyTorch, but yeah, we'll have to do it. So we have to assign these tensors, in this case inputs and targets, to a device, or the device that we are using. Okay, so inputs to device, and then we'll do targets dot to device. Okay, so now logically we'll have to go through two steps. So the first step is that of calculate loss, and the second step is to back propagate loss and update weights. Now, we are basically going through like the basic functioning of neural networks. So at each batch, we want to calculate the loss, and then we want to basically like back propagate the loss, and then use gradient descent for updating the weights. So doing like a full step of updating the weights. So I know like this is going to sound a little bit weird if you're not familiar with deep learning like theory and how like neural networks work, but if that's the case, don't worry, because I have a very detailed series on this, on the theoretical aspects of deep learning, and so you can check it out up here. It's called Deep Learning for Audio with Python. There I deal with a lot of stuff regarding like the theory behind deep learning and intuition, as well as the kind of like mathematical formalization of it. So just check that out if you need to. But now let's just focus on the PyTorch implementation here. Okay, so we want to calculate the loss. So how do we do that? Well, first we need to get the predictions with the current model. So we'll do a predictions is equal to model, and we'll pass the inputs. Okay, so we use the model quite simply like this. So we pass the inputs to the model and we get back our predictions. Good. Now, how do we calculate the loss? Well, for that, we have a loss function, right? And we haven't defined this yet, but we'll define it later. But for now, let's just talk about it or use it as an abstract loss function. Okay, so to the loss function, we want to pass two things. Of course, we want to pass the predictions and we want to pass the targets, right? So these are the expected values and these are the predictions. And what the loss function will do is comparing these two and come up with a loss. Okay, so now we have the loss. It's time to do a backpropagation and then apply gradient descent to update the weights. Okay. The first thing that we have to do, though, is take the optimizer, which is another entity that we haven't defined yet, but we'll do it later, and then apply this function called zero grad. So what's this zero grad? Well, at every iteration, the optimizer is going to calculate gradients that we'll need, of course, like to just like decide how to update the weights. What happens is that these gradients at each iteration get saved. Now, what we want to do is that at each training iteration, at each batch, we want to reset the gradients to 0, or in other words, 0 grad, so that we can start from scratch. So this is all 0 grad does. Okay, so now we've reset the gradients. It's time to actually perform backpropagation. So we'll do loss and then we'll call backward. Okay, and the final step will be that of taking the optimizer and doing a step. And what this final step does, it's just updating the weights, whereas this penultimate, like a line here, say loss.backward, just applies backpropagation. Cool. Now, once again, if you want to have like a better idea of how backpropagation and gradient descent work together in order to optimize or to train our models, just go and check out like this video up here where I talk about both backpropagation and gradient descent in quite a lot of detail. I give you the intuition of it as well as the mathematical formalization. Okay, now one thing that I want to do here at the end of this round of training for the epoch is to just print the loss. So what I'll do here is loss, and I'll pass loss.item. So what I'll be doing here is basically just printing the loss for the last batch that we have. Okay, so this is all we need for training one epoch. One consideration here. So if you're familiar with Keras and TensorFlow, you probably will notice that this is a little bit different in terms of like the overall approach. So many of these things are like taken for granted in a sense in Keras. So you have a very simple method, train, you just like call it and it takes care of all of this stuff under the hood. Here in PyTorch, it's not really like that, so there's way more detail to actually be compiled by you. So this has both pros and cons. Among the pros is that you have a lot of customization, a lot of control, but on the kind of like the flip side is that, of course, it warrants more code for you, and you really need to know what you are doing, right? So it's important that you know the theory, so you can't just use this as a very simple API without understanding what's going on under the hood. Okay, yeah, just this was a kind of like consideration on the difference between like different deep learning frameworks. But now let's go back to the implementation. So train one epoch is done. Let's move on to train. Now, train is quite straightforward because what all we'll do is just going through multiple epochs, and then at each epoch we'll be calling train one epoch. As simple as that. So here train would expect all of these arguments plus a final one that's epochs. That's, in other words, the number of epochs. So here we'll do for I in range epochs, and here we'll do print. We'll say epoch, and yeah, let me just make this an f string, and I'll say I plus 1. So here we just like print the epoch we are currently in, and then we call the train one epoch, and we'll pass all of these arguments. And finally, here we'll do, yeah, let's just add a separator for each epoch. Last bit, instead of printing a message saying training is done. Cool. Okay, so now we have train and train one epoch. So we are ready to train the model. So let's put it here in the script. So train model. And this is quite straightforward because we should just pass the model in, and the model is this one here. So feed forward net. Then we should pass the data loader, train data loader, then the loss function. Of course, we haven't defined this, but we'll define it in a second. Then we'll define the, well, we should pass the optimizer. Again, we haven't defined this, but we'll do it. And finally, well, not finally, because we still have two of this argument. So one is device, and the other one is epochs, number of epochs, which is going to be another constant that we'll define up here. So how many epochs do we want to train for? Yeah, let's say 10. Okay. Right, so here we still have to define loss function and optimizer. So let's do that. So let's instantiate a loss function plus optimizer. Okay, so let's start with the loss function. So the loss function that we'll be using is cross entropy loss. And then for the optimizer, we'll be using Adam. So we'll do a torch.optim.Adam, and here we should pass a couple of arguments. First of all, we need to pass the parameters that Adam, our optimizer, should optimize, right? And what are these parameters? Well, it's the parameters which come with feed forward net. So we'll take feed forward net, and then we'll call parameters. And so here we ensure that we pass all the parameters of feed forward network to the optimizer. And then the other argument is the learning rate. And this we'll define as yet another constant up here. So learning rate, and we'll just use 0.001. Okay, good. Okay, so we have everything ready to train the model. So of course, once you've trained the model, what you want to do is to store it, unless you want just to waste your training time, okay? So now let's store the model. And to store the model, PyTorch provides us with facilities that are very, very easy to use. We can do a torch.save, and then here we should pass a couple of arguments. So the first one will be the model itself, so feed forward net, but specifically we should get the state dict. So now what's the state dict of a model? Well, that is a Python dictionary that has like the state, so all the important like information regarding layers and parameters that have been trained. And then we should also pass the path to the file that we want to use to store the model. And here we'll just do a feed forward net net.pth. Okay, so in other words, we'll be storing the model in the working directory under like this a file name here. Okay, so torch.save. The final thing that I want to do is just print something saying model trained and stored at feedforward net.pth. Okay, so now we should be ready to run this, and if we haven't made any errors, then it should work fine. So let's see if it works. Let's run it. Yeah, it seems it's working fine. So we just started to train the first epoch. We got the loss for the first epoch, and now we are moving on. Okay, so I'll just pause the video and resume once training is done. As you can see, training is done and the model has been trained and stored. So let me show you where the model was stored. So here, this is the current directory, and here we have this feedforward net.pth file that stores all the important information regarding our neural network. That's it for this video. If you are wondering about how we can load the model back and use it for inferences, well, that's the topic of the next video. So remember, these two videos will be a kind of initial contact with PyTorch, and then after this we'll be delving into more advanced topics, also dealing with audio. Okay, so I hope like this was like valuable for you. If that's the case, remember to leave a like. If you have any questions, as always, please feel free to leave them in the comment section below. And if you have like doubts and you want to just like get more ideas and ask questions, you can join the Sound of AI Slack community, and I'll leave you the link to the community in the description section. Okay, that's all for today. I'll see you next time. Take care. Bye.